Hi, welcome to Hubble's Universe Unfiltered. I'm Dr. Frank Summers. I work here at the Space Telescope Science Institute in Baltimore, Maryland. And because we're the scientific home of the Hubble Space Telescope, sometimes friends or relatives when they're visiting say, hey, can we come down and have a look? You know, they want to come down to the Institute and they want to see the telescope. Well, unfortunately, the telescope's not here. The telescope's up there, about 400 miles above our heads. The telescope is a space telescope, and a lot of times people sort of forget that. And really, if I bring them here, there's not that much to see, because it's an office building. We're a bunch of scientists. We work on computers. I'm sorry, it's not the most exciting thing to see geeks typing on computers. We do have a few interesting things here, but really, if you come to Baltimore, where you really want to go is this place. This is the Inner Harbor of Baltimore, and it's a wonderfully redeveloped district in downtown Baltimore where there's shopping, there's paddle boats you can go out onto the Inner Harbor, there's some museums, there's a wonderful aquarium, and really this is the tourist mecca of Baltimore. Now, you might be asking yourself, all right, so what's he doing this commercial for Baltimore for? When's he going to get to the science? Well, what if, to do a scientific visualization, what if a black hole decided to visit Baltimore's Inner Harbor? This is a scientific visualization that we did here at Space Telescope to try and show the effects of what a black hole would look like if a black hole came in across the Inner Harbor. And here's what it looks like. Now, you notice in the beginning that it looks relatively normal. Everything looks straight, looks the same. But over here on the left-hand side, you begin to see the black hole passing into the picture. And it's passing across the water in between you and the buildings. And you can see the buildings become all distorted. But once it passes through, your view of the buildings returns to normal. So what's going on here? Well, a black hole is a lot of mass crammed into a really, really small space. It's extremely dense. It is so dense that it actually warps the fabric of space. And so when you look past a black hole, you're looking through warped space. So with a black hole out here hanging over the water, your view of the buildings in the background gets distorted. We call this gravitational lensing. The gravity of the black hole is so strong that it warps space, and light traveling through warped space has all these distortions. So you can see that if you look to the right of the black hole, you see this building over here on the left. Likewise, if you look to the left of the black hole, you see this building over here on the right. You look below the black hole, you see the sky. You look above the black hole, you see the ground. These distortions in space distort the light passing around it, and so your view around a black hole would be distorted. And we use these scientific visualizations to give you a real-world example of what happens in astronomy. Now, we don't have any black holes nearby to take a look at, but these gravitational lensing effects also occur for clusters of galaxies. And nowhere does it occur better than for this cluster of galaxies, Abell 1689. This is one of the most massive clusters of galaxies anywhere in the universe, and there is so much matter in this cluster of galaxies that there is enough density to produce gravitational lensing. Now, how does this work in the universe? Well, here we are here on Earth, and we're looking out past this cluster of galaxies here, and we'll be looking at a distant galaxy over here. And the light from this distant galaxy will have to pass through this warped space around this cluster of galaxies before it reaches us here on Earth. So the light could actually go over this side and it'll get a little bit deflected and we'll be able to see it. Or it could pass around the other side and get deflected and we'd see it. And we can see multiple images of the same galaxy. Plus, just like you saw in the previous example, the light would get distorted. In the case of the clusters of galaxies, the light from distant galaxies gets distorted into these long, thin arcs. We call them, relatively straightforwardly, gravitationally lensed arcs. And the big yellow blobs here are the galaxies of the cluster, and these long, thin streaks that you see here and over here and all throughout this image are these distant galaxies whose light has become stretched and distorted while passing through the space around this cluster of galaxies. And there's even more than that, because remember how I said it could pass one side or the other, and you'd see two images of the same galaxy? You can actually see that because this blue streak here and this blue streak over here are two images of the same galaxy. A galaxy much further beyond this, whose light is passed to the left and to the right of the cluster, and we see it in two different places on the sky. How cool is that? What's even more cool is you can call this visual proof of general relativity. Because Newton's theory of gravity doesn't involve any distortions of space-time. Einstein's theory of general relativity does. And when you interpret gravity as a distortion of space-time, you naturally get such gravitational lensing artifacts as a result. And the fact that we see these gravitational lenses shows you that general relativity is the correct theory of gravity. So even if you've never even heard the equations of general relativity, you can now say to your friends, hey, I know it's true because I've seen these gravitationally lensed arcs. There's one other thing that's really cool about gravitational lensing in this image, and it occurs over here. Now, we took some new data of this region, and this data is not really as pretty as this. This is a nice color picture, but the data of this region is simply black and white. All right, this is a visible light image of this region, and here you see one of these gravitationally lensed arcs. But the really cool thing is what you don't see right here. There's a lot of nothing here, and the fact that there is nothing is actually kind of cool. Because this is a visible light image, the same light that your eye sees, but if we move to infrared light that Hubble can see, you start to see a little bit of something here, okay? Infrared light has a little bit longer wavelength than visible light, and we start to see an object appear here. If we then moved even farther into the infrared light and we use the Spitzer Space Telescope, we see a really interesting blob of material. Now, yes, it's just a blob, but it's a really interesting blob. And it shows up brightly in the infrared, but it doesn't show up in the visible. This tells us something really important. Now, this blob is well on the other side of the cluster. Matter of fact, we couldn't see it unless the gravitational lensing were there, because the gravitational lensing amplifies the light, makes it much brighter than it otherwise would be seen. This blob is about 12.8 billion light years away. Billion with a B. That's almost the opposite side of the universe. Okay? And that means we're seeing this object as it was 12.8 billion years ago, because light travels 1 light year in a year. It takes 1 year. So if the object is 12.8 billion light years away, it's taken 12.8 billion years for that light to travel across that space. While the light has been traveling across that space, the universe has been expanding. Okay, the size of the universe is getting bigger. The light traveling across expanding space also stretches. So the light left this object, probably in visible light, and then it stretched as the universe expanded and now becomes infrared. That's one of the ways we can tell this object was a candidate for being a very distant object, the fact that we could see it in the infrared and we couldn't see it in the visible. Okay, we didn't know how far away it was when we first found this object, but by seeing it in the infrared and not seeing it in the visible, we could flag it as a candidate for follow-up study, and in that follow-up study we discovered that it's 12.8 billion light years away. This object is an early galaxy, a galaxy that is just beginning to form. I mean, I'm not sure I could even call it a galaxy yet, because it's just the stuff of a galaxy beginning to come together. Okay, something that's only a few 100 million years old, less than 1 billion years old, and it wouldn't really develop a good galaxy structure for about 1 billion or 2 billion years. But what is really cool about the whole thing is that with the gravitational lensing, creating the arc here, but magnifying the image of this object, we would never be able to see this object at all if it weren't for the gravitational lensing amplifying its light, making it visible through the gravitational lens. So, by using the gravitational lensing, we can see all sorts of cool things. We can see these arcs, we can see multiple images of galaxies, and we can see galaxies that we otherwise would never see. Galaxies on the other side of the universe. So there's plenty out there to discover, And it's amazing the number of different ways that we can discover interesting objects in Hubble's universe. Take care. We'll see you next time. Frank Summers. I work here at the Space Telescope Science Institute in Baltimore, Maryland. And because we're the scientific home of the Hubble Space Telescope, sometimes friends or relatives, when they're visiting, say, hey, can we come down and have a look? You know, they want to come down to the Institute and they want to see the telescope. A fully redeveloped district in downtown Baltimore, where there's shopping, there's paddle boats you can go out onto the inner harbor, there's some museums, there's a wonderful aquarium, and really this is the tourist mecca of Baltimore. Now, you might be asking yourself, all right, so what's he doing this commercial for Baltimore for? It's an office building. We're a bunch of scientists. We work on computers. I'm sorry, it's not the most exciting thing to see geeks typing on computers. We do have a few interesting things here, but really, if you come to Baltimore, where you really want to go is this place. This is the inner harbor of Baltimore, and it's a wonderful. Well, unfortunately, the telescope's not here. The telescope's up there, about 400 miles above our heads. The telescope is a space telescope, and a lot of times people sort of forget that. And really, if I bring them here, there's not that much to see, because Hi, welcome to Hubble's Universe Unfiltered. I'm Dr. Frank.